Hello everyone, welcome to this video. In the previous video, we have seen what are reducible and irreducible polynomial. In this video, we shall see a reducibility test when the given polynomial is of the degree 2 or is of the degree 3, right? So what is the result or what is the theorem? Theorem is if f is any field, this is the given field, and we have some polynomial in that field, right? Polynomial ring, and degree of this polynomial is either 2 or 3. In that case, this given polynomial fx, this is reducible over f if and only if it has some 0 in the in the field f. So this polynomial is reducible only if it has a root, or if it has a root, then we can say that the given polynomial is reducible polynomial over the given field. So let us see the proof, right? So this is an important result which we can apply frequently to see if the given polynomial is reducible. So firstly, we'll assume that the given polynomial is reducible, and then we shall prove that it has a 0 in f. This is one way of the proof. The other way would be we'll assume that this polynomial has a 0 in f, that is, it has a root, and then we shall prove that this polynomial fx is reducible. So as for now, let us consider that this is a reducible polynomial. So that means by definition we can write this as the product of two polynomials where the degree of each of these polynomials is less than the degree of the given polynomial fx, right? So now we are saying that at least one of this gx and hx, it has at least one of these has degree 1. How this is so? Because we know that there's a result that in fields, degree of the polynomial fx is equal to the degree of the polynomial gx and degree of the polynomial hx if they are written as the product of two different polynomials, right? So in this case, our given polynomial f has degree either 2 or it has degree 3, right? So what are the possible degrees for gx and hx? So if this degree of fx is 2, in that case gx could be 1 and hx could be 1 because they are less than the degree of fx, right? If the degree is 3, there are two possibilities. Either gx has degree 2 and hx has degree 1, and the other way around, right? So in each of these cases, at least one of g or x or hx has degree 1. So we assume that gx is of degree 1, and that means it would be some linear polynomial of this kind. So now when could we say that this polynomial is 0? When ax plus b is equal to 0. So that means the root of this polynomial would be minus a inverse b, because when you plug x is equal to minus a inverse b into this polynomial equation, you'll get 0. So that means this is the root of gx. If you found one root of gx, that means when you put that value into this polynomial, this term would be 0. So ultimately this would also be 0. So we can say that this value of x is also a root of fx in f. Why in f? Because these coefficients were in f, capital F. So this x is also in capital F. So that means you found a root of fx in the given field, right? So this is one way of the proof. So let us prove the other way around. Now let us assume that fx has a root and we are to prove that fx is reducible, right? So we assume that a is the root of this polynomial. So that means f of a would be 0, right? So if a is a root, that means x minus a is a factor of the given polynomial fx. So that means what you are saying is when you divide the given polynomial fx by x minus a, right, whatever is this gx, let's call it hx, the remainder would be 0, right? So by division algorithm, we can write fx is equal to h minus x minus a multiplied by some other polynomial, whichever is the question polynomial, say hx, where the degree of hx is less than the degree of fx, so that we can say that fx is reducible, right? So this is the result. So let us look at one example. The example is that this polynomial x square plus 1, this is irreducible in Z3 but reducible over Z5. So now how can we check this? This polynomial has degree 2, right? So that means we can apply the above result onto it. And moreover, to check this is reducible or irreducible over these two fields, it is sufficient to check whether this polynomial has some root over these fields, in this fields, right? So now the field Z3, it contains the elements are 0 bar, 1 bar and 2 bar, where these are the equivalent classes, and Z5 contains the elements 0, 1, 2, 3 and 4 as the equivalent classes, right? So now to check whether this polynomial has a root in the given field, what you need to do, you need to check that whether 0 is a root of this, whether 1 is a root of this, or whether 2 is a root of this. What does that mean? That means that when you substitute this value in place of x into this equation, whatever is your answer, if it is 0, you say that it is a root, otherwise it is not. So let us get started. Let us calculate this for the given field Z5. So for Z5 we have these elements. So let's check it one by one. So what would be f of 0? It would be 0 square plus 1, so that will be 1, and that would be 1 mod 5. That means when you divide that by 5, you will get the answer as remainder as 1. So what would be similarly, let's see f of 2. So what would be that? 2 square plus 1, so it would be 5. So when you divide 5 by 5, the remainder would be 0. So it is equivalent to 0 mod 5, right? So you get 0. So that means you can say that this 2 is a root of the given polynomial in the field Z5, right? So this is one root. So similarly, you can check for 3 and 4. So you saw that this 2 and 3, they are the root of this polynomial in the finite field Z5, right? So you find two roots. Basically, the theorem said if you get one root, then you can say that it is reducible in Z. So we have enough. So we can say that it is reducible in Z5. But this is not the case when you replace the field by Z3. So let us see. In Z3 we have elements 0, 1 and 2. So for 0, your answer is 1, which is 1 mod 3. For 1, your answer is 2, which is 2 mod 3, and for 2, it is 5. So when you divide 5 by 3, you will get the remainder as 2. So that means it is also not a root. So you do not have any root of this polynomial in Z3. So that means you say that our polynomial is not reducible in Z3, or in other words, it is irreducible in Z3. So I hope it is clear. So now let us look at the case when the degree is greater than 3. That means it is 4, 5 or 6. So can we again apply the same result onto that polynomial? I am afraid not. So here's a note. Polynomials of degree greater than 3 may be reducible even if they do not have a root in the field. For example, we have this polynomial x raised to power 4 plus 2x square plus 1, and the given field is the field of rational numbers, right? So now this polynomial do not contain a root in this field, because when you see this, it would give x is equal to plus minus iota and minus plus minus minus plus iota, right? So it would be minus plus iota. So these would be the two roots, right? So you clearly see that the roots are not present in the given field, the field of rationals, but it is clearly reducible because you can write your given polynomial as product of two polynomials whose degrees are less than the degree of the given polynomial. So it is clearly reducible polynomial. So this result is not valid for polynomials with degrees greater than 3, right? So I hope this is clear. So next, let us look at Gauss lemma. Remember what is the definition for primitive polynomials? The polynomials which where the GCD of all the coefficients is equal to 1, right? And it is defined only for those polynomials where the coefficients are being taken from the set of integers. So this Gauss lemma says that the product of two primitive polynomials is also primitive, right? So we need to prove this. So let us consider two polynomials. One is fx, which is written as this polynomial having coefficients ai, and let another polynomial be gx with coefficients bj, right? These ai and bj's are from the set of real numbers, and we have considered this to be primitive polynomials, and we need to show that the product of these two polynomials, that is fx into gx, is not primitive, is also primitive, right? So we will prove this by the method of contradiction. So we shall assume that if possible, let this product is not primitive. If it is not primitive, that means there exists some number p which divides all the coefficients of p, right? An irreducible element which divides all the coefficients of this polynomial, right? Fx and gx. So because these two polynomials are given to be primitive, that means this p cannot divide any coefficient of the polynomial fx and any coefficient of the polynomial gx. So I have called these coefficients as and bt respectively in the polynomials fx and gx. So because these are primitives, so this p won't divide as and this won't divide bt. So now let us consider this polynomial fx multiplied by gx, and let us see the coefficient of a particular term x to the power s plus t. So this term would be available because there is a term in fx having x to the power s, and there is a term in gx having x to the power t, right? So this term is obviously in the product fx into gx, and its coefficients would be something like this. This you know by the definition for multiplying two polynomials, that these indices, the sum of these indices should be equal to s plus t, right? So this is the case in every term. So there is no problem in writing like this. So now this is some previous result that the set of reals, this is a unique factorization domain, and in unique factorization domain every irreducible element is prime. So this gives us that this p is prime. Whatever p we have assumed, this is a prime number. So now we have assumed that because fx and gx are primitive, so this p does not divide as from here, and this p does not divide bt from here, right? So this also does not divide the product. You can see an example for this. Suppose we have a prime number 3, right? It does not divide 7. It does not divide 11, right? So obviously 3 won't divide 77 also, right? So there is no problem writing this. Therefore, we say that this p does not divide this term. If it does not divide this term, that means it does not divide whole of the sum, right? And if it does not divide whole of the sum, so this gives a contradiction to the assumption that we have assumed that p divides all the coefficients of the product polynomial fx into gx. That means we got a contradiction. So that means whatever we have assumed, is not true, that means this polynomial is not primitive. Therefore, the polynomial fx into gx is not primitive is not correct. That means we have assumed it wrong. So therefore, this product is surely primitive. So this was this was the result which we shall use in the upcoming results about irreducibility of involving polynomials with integer coefficients, which shall be the topic for our next videos. So that is it for this video. Thank you for watching.